Can you see the slides?
Yes, yes.
Okay, excellent. Okay, yeah, I'm a postdoc at Berkeley with Sergey Levin, and today I'll talk to you about my past and ongoing work learning to forecast and control agent behavior with visual data. Okay, so why should we forecast? We can take motivation from the natural sciences. They seek to build understanding through testable models of cause and effect. These models make predictions about the observations we should see, and if the future they've predicted comes true, we say the model is useful. So, for example, different models of gravity have been used to plan rockets to the moon and predict gravitational lensing. And morphogenesis models predict patterns of natural phenomena like fish scales and population dynamics. The empirical sciences structure understanding of the world through prediction. Another source of motivation for forecasting is human intelligence. Humans often structure their world around prediction. I claim that in order for an agent to be intelligent, it must have a reasonable idea of how the future will unfold. Humans process rich observations of their environment in order to understand and to behave. So for instance, we have the capability to predict and plan actions necessary to walk. We strive to predict how our competitors will behave. We can predict and plan socially acceptable driving behaviors. Our success generally depends on our ability to forecast. We usually fail when we can't. So it's worth noting that humans are particularly good at predicting the behaviors of other agents. And much of my research stems from my belief that in order to build intelligent agents that behave well, we must enable them to predict the future. So I'll talk to you today about my efforts to computationally model the future in the presence of agent behavior, given rich observations of the environment, like images. So I'll describe our goal in terms of a decision-making system that we want to build. So it should process high-dimensional observations of the environment to forecast sequences of multi-agent behavior. We should be able to direct this system by providing it with high-level goals to yield interpretable plans of behavior that we then execute in the environment. We can design the learned computational model in terms of the two types of outputs we want to generate. So one way to visualize some of the work I'll talk about today is in this 2D space that spans these desired output capabilities, forecasting and control. So I'll first talk about a generative modeling framework to perform motion forecasting of trajectories composed of continuous positions. This framework serves as the building block for a lot of the components of the rest of the work. So with this component's ability to forecast the future, the overall system should also be able to output explicit interpretable plans for how the system intends to achieve some goal. So here we have a learner generating and executing motion plans by choosing between high-level goals. This work illustrates one way in which a predictive model can be used to evoke some useful behavior. So our system should be able to reason in complex environments, specifically in environments containing other agents. I'll talk about another work that builds a multi-agent model of agent futures and show how it can be used to perform a task that it was never trained to perform, which I call conditional forecasting. So key to this idea is that the resulting predictions for all of the agents are made jointly as opposed to being decoupled. Then I'll talk about some work that extends our previous control work to be more robust to out-of-distribution scenarios, which are common in settings like autonomous driving. So we developed a method to perform planning under epistemic uncertainty, which allows the model to both identify as well as generate more robust controls in these out-of-distribution scenarios. Then I'll talk about one way to produce richer structured output with the model. The application domain here is first-person behavior modeling. The model can jointly learn and generate discrete and continuous trajectories of future behavior, which helps it better describe different aspects of behavior. Finally, I'll talk about some work on inverted forecasting, where instead of using the sensor data to detect the objects and then predict their trajectories, we instead predict the sensor data and then detect objects in the predicted sensor data. So basically the outline of the talk is covering each of these approaches in this space of forecasting and control. So first up is this generative modeling framework to perform motion forecasting of trajectories composed of continuous positions. So our target domain here is the future motion of vehicles. Throughout this section, the red curves are trajectory predictions for where the vehicle that's observing the scene will go. The blue curves are the true trajectories for where the vehicle actually goes. The model is a probability distribution over future trajectories, conditioned on LiDAR information about the scene. The natural images here are for visualization purposes, just in this model, but we have other models that also condition on these images. So here's a bit of notation. We represent trajectories as fixed length sequences of continuous positions, and we represent input observations as a set of past positions of the car and LiDAR features of the scene. Because the future is uncertain, we'll design our model, Q, to be a probability distribution. The distribution is over future trajectories and observes the input information. The distribution we're trying to match is a distribution of demonstrated trajectories, P, which I'll call the expert or the data distribution. In order to learn Q, we'll need to choose some objective function to measure the difference between P and Q, and we'll need to build Q efficiently to both efficiently learn and generate data. So let's look at some ways to measure the difference between P and Q in terms of cross-entropies. So the cross-entropy is a function of two distributions. It depends on the input ordering. One distribution is used for generating samples, and the other is computing log densities. So given the data distribution P and the model Q, this means there's two cross-entropies, a forward and a reverse. The forward and reverse cross-entropies have complementary properties. The forward cross-entropy, which corresponds to your standard maximum likelihood training objective, penalizes false negatives very heavily, which is failing to assign high likelihood to the data. So it penalizes failing to assign high likelihood to the data. But the forward cross-entropy is insensitive to false positives. It hardly penalizes the model for generating bad trajectories. The reverse cross-entropy instead heavily penalizes the model for generating bad trajectories, but it's completely agnostic to whether all of the modes are covered. It's agnostic to false negatives, failing to predict all of the plausible outcomes. So if we train a model with just the forward cross-entropy, we end up usually covering the expert, but sometimes generating some bad samples, like off the road here in this example. If we train a different model with the symmetric objective, we will generate bad samples less often. Here, the yellow indicates a high cost under a prior model, P tilde, which is telling the model the expert doesn't usually go here. So the model ends up internalizing that samples rarely, and then therefore rarely generating samples that go off the road. Okay, so we have our two terms that form our symmetric objective. Let's turn to designing our model, Q, to optimize this objective efficiently. In order to evaluate the cross-entropy, the forward cross-entropy, we need to compute the model's probability density function efficiently. We also need to be able to optimize the model smoothly to smoothly adjust its samples according to the feedback from P tilde. So we need to be able to compute the gradient of our samples with respect to the parameters of the model. So by implementing Q as a normalizing flow, we can actually satisfy both properties. It can efficiently compute the density function and smoothly adjust its samples. If you're familiar with VAEs, a normalizing flow also employs a known base distribution, usually a normal distribution, and it uses samples from this base distribution as input to a parametric warping function that creates samples in the output space. So what's different between VAE and a normalizing flow is that if we make this simulator function, this warp, invertible and differentiable, then we can compute the output distribution density in closed form. So how do we design this forward warping function? It must be invertible, differentiable, and parametric, learnable. So I will actually skip most of the low-level details, but one key feature of the design is that we design it to be autoregressive. So it sequentially generates positions in the output trajectory. And this results in an equivalent representation of the density function as just a product of sequential normal distributions. The parameters of each normal distribution are predicted as functions of the previously generated positions and the scene observations. So this gives us a high capacity model capable of generating complex multimodal trajectory distributions. The key here is that mu and sigma, these outputs from the neural networks, react to the partially generated trajectory and to the scene information. So I'm going to skip over the implementation of mu and sigma, which is detailed in the paper, and then instead move on to the next work. So the last method that I just described is a method to predict the underlying motions of high-level activities, but it did not execute any controls after forecasting. So if you recall the end system we have in mind, we want our models to both forecast and execute controls in some environment. So let's say we would like to learn a complex task, like driving a car. We could collect a lot of data from human drivers to help us learn this task, but what should we extract from this data? We could simply imitate the human drivers by doing the thing that we think the human is likeliest to do. This can work well when the thing that the human is likeliest to do is exactly what we want our robot to do. But if we want the robot to do something else, like instead of at this intersection turning right, we want it to turn left, how do we do this? We can't directly apply imitation learning in this case, as the estimated likeliest human behavior doesn't align with the task of turning left. A model learned via imitation learning is generally difficult to direct to new tasks. However, imitation learning has the benefit of not requiring a reward function to specify behavior. We've just learned from demonstrations, and it generates some behavior. So alternatively, if we consider learning a dynamics model and planning an action sequence under it, as in model-based reinforcement learning, the method can adapt its plans to different tasks using a provided reward function. However, this relies on the ability of the practitioner to design a reward function, which is generally very difficult to do, especially in complex settings like autonomous driving. So the idea behind our approach is that we can use data to constrain a model-based reinforcement learning method so that it only plans paths that are similar to those that the human demonstrator would have used. In the driving scenario, this means that the human drivers teach the model about the rules of the road, while model-based planning enables it to reach the desired test time goal. So to use a deep imitative model, a data set of expert data is collected first, so demonstrations of driving behavior. Then the deep imitative model is trained to forecast this behavior, essentially just perform the forecasting task that I described in the first part of the talk. So this forecasting is done conditioned on information about the scene. And again, in our application, we use past states and LiDAR information as inputs to the model. A key aspect of this model is that it can evaluate the density of arbitrary trajectories. We talked a little bit about that in the previous section, where the model can compute the probability, its probability density function exactly of any arbitrary input, and will make use of this as part of the optimization criterion during planning. So once we have this model learned, tasks are specified to the model in terms of these likelihood functions on top of trajectories. So for example, an indicator function on the final state of the trajectory tells the robot its goal is somewhere in the provided set of acceptable goals. Here, that set is a goal polygon. So the task and the model together define the optimization criterion that's used to plan what it thinks the expert driver would do to achieve this task. So here we see the resulting plan is turning left, following the course directions of the task specification, while determining the fine-grained details according to the model of expert behavior. We can consider different tasks too. As long as they can be specified as a function of a trajectory, then we can apply a deep imitative model to it. Here the task is to navigate to one of several goal positions while avoiding potholes specified as a cost map. The best plans look as expert-like as possible while still achieving the joint objectives of avoiding potholes and navigating to a goal position. So note here that the expert didn't necessarily need to demonstrate any behavior of what it means to avoid potholes. If we can specify the goal objective in terms of trajectories, then that we do observe generalization to an extent to new objectives. Essentially, in this case, the car is able to navigate to these goals, avoiding potholes, while it never had observed any demonstrations of what it means to avoid a pothole. So how do we do this planning? How do we combine the model's density function with how we're specifying the goals? So we perform planning as inference by performing map estimation on a posterior that measures the probability of the plan given the goal, G, and the scene, phi. So by applying Bayes' rule, we receive two relevant terms. The first is where we use the imitative model as a scene conditioned prior. And then the second is the goal likelihood, which specifies the task objective. So let's take a look at some example goal likelihoods. Goals can be specified, for instance, as constraints on the positions of the trajectory. For instance, we may constrain the final position in the plan to end at one of many states. You could think of these states in our application as being outputted by some higher level path planning system like Google Maps. So that outer system is not necessarily aware of what the positions of the other cars or general dynamic objects of where they are on the road, or the state of the stoplights, or the precise position of the curve. This outer system is just giving us very coarse directions that includes which way to turn at each intersection. So instead of individual positions, we could also constrain the trajectory to end along some line segment. As shown before, we can also specify that the trajectory must end within a particular goal region. So here you can see the trajectory leaves this orange region midway, but succeeds in planning to end within that region. Here's another example of region goal likelihood planning. The goal region here just specifies the lane that the car should drive in, and then the model decides to keep the car stopped because it observes another car in front of it with its high dimensional observations. Here's another example where the region is much larger, but the model keeps the vehicle to stay in the correct lane. Note there are many places within the provided goal region that would correspond to a bad final goal to have, like going in the wrong lane or going off the road. But the plan from the model respects the goal and otherwise chooses the most expert-like behavior that respects the goal. And so that expert-like behavior it has internalized respects the rules of the road. Here's another example of that. The model plans to move forward and stop behind another vehicle. The model is rarely distracted by these erroneous goals, like those I mentioned in the wrong lane or off the road. Essentially, the main requirement of these goal likelihoods is that there's at least one expert-like behavior that's likely under the provided goal distribution. So here the plans, it's the pothole driving objective again. The plans are avoiding potholes as specified by a cost map to arrive at some set of goals. So we can actually mix these goal likelihoods together as a way to essentially incorporate sort of more sophisticated constraints or specifications on what behavior we want the system to evoke. So we tested our system by evaluating on the CARLA autonomous driving simulator, and specifically on their dynamic benchmark in training and evaluation towns. So in the dynamic navigation benchmark, there's other cars in the scene that we have to deal with and not run into and whatnot. So we find that many variations of our method outperform prior work in model-based reinforcement learning and imitation learning approaches. Actually, on the test data, it's outperforming prior work by more than 20% in terms of absolute performance. And many ways to command the system to provide goal likelihoods are fairly successful at this task. So here's a video of the approach running in CARLA. The model automatically learns that the expert prefers to stop when there are vehicles in the way or when it encounters a red light. And it predicts trajectories that exhibit other expert-like properties like achievable velocities and staying on the road. Even if the goals are poor quality, like if they're on the wrong side of the road or there's a lot of noise in them, the approach is able to smoothly determine a trajectory that does its best to achieve them while still being as expert-like as possible. So on the left here, the goals are actually on the wrong side of the road in this town, but the model in the system is still able to make use of them because they provide course direction to where to steer the vehicle. And then on the right, half of the goals are essentially decoy goals, highly perturbed versions of the original goals. But the goals that the model ends up choosing as its preferred goals are those essentially it's rarely fooled by the noisy goals. Okay, so that was great, but one of the drawbacks of that system is that it did not explicitly model the future behaviors of the other agents. Essentially, it was just marginalizing out the behavior of the other agents in the scene. But we want a system that's capable of reasoning in complex environments, specifically in environments containing other agents, and where their behaviors are more sophisticated and we need to explicitly reason about them. So I'll talk next about another work that builds a multi-agent model of agent futures, and then I'll show how it can be used to perform a task it was never trained to perform, which I call conditional forecasting. Key to this idea is that the resulting predictions for all of the agents are made jointly as opposed to being decoupled. So the question that drives this next work is, how can we reason about multi-agent behavior when we have control of one of the agents? So many settings generally involve complex interaction between agents, and we want to automatically capture these complex interactions in order to predict future behavior. This video is a demonstration of our approach to predict the future motion of many agents in real traffic scenarios. In mobile robotics settings, a very common pipeline involves forecasting the behaviors of the other agents without knowledge of the controlled agent's intention. However, in these settings, we generally have knowledge of what we want our robot to do. We have control over the robot's intention. So our framework has the capability to leverage this additional source of information to inform its predictions. By incorporating knowledge of our own robot's intention, we can reason about how other agents might respond to our intentions. I'll show that this enables us to forecast what other agents could do with greater accuracy. In our application, this means that we can better forecast what other human-driven vehicles are going to do, given knowledge of our own autonomous vehicle's goal. So it's critical for us to model and evaluate the approach in terms of joint behavior. Let's look at a simple problem with just two agents. Imagine I'm driving the blue car at an intersection and I want to turn left. If the orange car gets in my way, I need to react to their behavior in order to avoid bad joint behavior, like a crash. Because the behavior of agents is codependent, we need to both model the data and evaluate the data with this joint interactive behavior in mind. If we don't model any future interaction between them, individually likely behaviors can yield unlikely joint behaviors. So similarly, if I evaluate the forecasts on a per agent basis alone, then the evaluation is going to fail to penalize situations that rarely occur when other agents are present. The takeaway is that we can't independently model or measure forecasted behavior. You have to do it jointly. So I'll relate the outputs that you see here to the graphical models that created them. The model on the right correctly captures interactions at every time step between each agent, which allows the forecasted agents to sequentially react to each other. The model on the left incorrectly decouples the future decision-making of the agents. So the samples on the left are coming from this decoupled model. Sometimes it generates the samples on the right, but half the time it's generating those samples on the left. So there's several ways that we can use the model on the right to forecast behavior. Let's look at them now. So here I'm displaying the examples of standard forecasting with our model, essentially just sampling from it. The model can make joint predictions for where all of the cars could go. The paths marked with circles indicate possible future motion. The paths marked with triangles indicate past positions. If they're hidden for a vehicle, it just means the vehicle was stationary in the past. So let's now leverage the fact that we have control over the robot car, that car 1 in blue. We should use knowledge of our robot car's intention when making predictions about the behaviors of the other human cars. So I call this problem conditional forecasting, and it essentially corresponds to intervening on the agent's goal in the probabilistic model, which is exactly what we do when the robot is allowed to choose its own goal. The approach I'll describe to you soon lets us perform these conditional forecasting, this conditional forecasting task. So we can set any agent's intention and consider how that would affect the predictions of the other agents. For instance, if we control the robot car 1 to drive faster than it would otherwise, the green human car 3 behind us is predicted to usually move faster. If instead we plan the robot car 1 to stop at some time far in the future, so we know we're going to be stopped for a long time, the human car 3 is predicted to usually stop in response. These predictions show that the model captures aspects of the interaction between agents. So now I'll talk about how our model makes these predictions. So it's very similar to the prior model I described to you, except it is applied to multiple agents, as well as it captures interaction terms between the agents. So it models behavior as a sequence of stochastic decisions of every agent in the scene. So in order to do this, we factorize the model over the agents and over time and provide it with the scene context as before. The factorization property is key to implementing the conditional forecasting capability of the approach. The latent states, I call them latents loosely, but let's just, they're not actually latents in a latent variable model because it's a normalizing flow, but these Z's, I'll call them latents, correspond to an agent's control of the next action that it can take. So given my observations of the scene and of all other agents' positions up until now, the Z is the final determination of what my next state is going to be. So if we decide latent values from one of the agents, like our robot car, then we've specified how the robot is going to react to what it sees in the future. In order to perform conditional forecasting, we are going to choose these latent Z values for the robot that takes the robot's goal into account. Once we've chosen the Z's, we'll pass them into the forward inference procedure. So essentially, knowing the Z's pins down all uncertainty and bijects to a single joint trajectory prediction. So the model is again implemented as a normalizing flow, which enables us to compute the required density function of S. And we'll use this density function to recover good Z's that identify or that achieve goals. So we perform prediction condition on goals, or PRECOG, as follows. We first plan the robot decisions according to an objective that I'll describe soon that takes the goals into account. Then we sample latent decisions for the humans. We sample the Z's of the humans, and then feed the joint latent values into the forward simulation of the model that generates output states, an output joint trajectory. So now I'll talk about how we design this objective L that enables us to achieve the robot goals in terms of its latent states. So if we actually go back to our deep imitative models objective, we apply Bayes' rule again, except it's a slightly different posterior that we essentially have to factor in that we cannot control what the other agents are going to do. So we have to marginalize out over, their source of uncertainty. And we end up with two terms here inside that expectation. Again, we have this prior, but it's a multi-agent prior instead of a single agent prior. And again, we have this goal likelihood term, which is how we're going to specify the agent's intentions. We perform planning on this approximately by just running stochastic gradient ascent, sampling the human Z's, taking gradients of the objective with respect to the robot Z, and then choosing the robot Z that maximizes this. So what did we do for the goal likelihood? We actually used a pretty simple one, which is we just placed a normal distribution about a point. So in cases where we know the final position of the robot, this enables us to say your Z's are good if they end at if they usually lead to you achieving this final position. So that was the goal likelihood behind the earlier examples that I showed you. Conditioning on different robot goals gives us different joint trajectory samples. And here are some examples of that same procedure going on in the real data. So in the top example, conditioning the predictions on the robot goal yields a sample batch where the other car moves to take up the space. It's vacated by the otherwise close following robot. So on the top left, the robot under the prior is moving faster, the robot in blue. And then on the right, we're saying, oh, the robot's going to move a bit slower. And then you can see the samples of the human in orange sometimes move to take up the space that's vacated by the robot. In the bottom example, conditioning on the robot's goal to stop yields a sample batch where the other car behind the robot is predicted to also stop. So on the left, again, it's just the standard forecasting, sampling from the prior. And then on the right, these are samples from the approximately maximized posterior that's marginalized out the human sources of uncertainty. So when we sample the Z's, there's still some stochasticity in what could happen, but it's here you can see in this example, it's reduced. So is this useful for anything? We measured whether we could make better predictions of the other agent's futures if we're given knowledge of the robot's own future final position. So in all the experiments we ran, we found that this knowledge was helpful for making better predictions of the other agent's future trajectories. We also evaluated against various competing methods for multi-agent vehicle forecasting on a few different data sets and found that our method outperformed them in terms of the sample quality and for the approaches they measured it, the test log likelihood. So again, we're measuring the quality of the joint trajectory predictions because of the earlier discussion about how individual evaluation is insufficient because individually likely trajectories can yield bad joint trajectories. So our approach has several variants. One of the variants here is ESP road flex, which is flexible to a dynamic number of agents in the scene. As long as the number of agents in the scene is less than some pre-specified parameter, we can incorporate and adjust the model's predictions with the same model to having a different number of agents. And here are a few more qualitative examples. The standard forecasting, basically just from the prior, captures many modes of behavior of many agents in the scene, and we observed it to perform well across a large range of situations and data sets. And I encourage you, if you're interested in this, to check out the paper. There's many more visualizations that can be helpful for understanding what's going on. Okay, so we have this model that can predict multi-agent behaviors. But let's go back to the case where we are only modeling the behavior of our own agent. We're predicting the future of our own agent. But the task is now to be more robust to out-of-distribution scenarios. In most real-world applications, the space of tasks, like the thing on the right in red, is inexhaustible. It's much larger than the space of training data that you observe. So for an example, an agent trained in one city on the East Coast in the United States may have a hard time dealing with the driving norms and the road morphology in places on the West Coast. So these two figures illustrate the failure of the previous approach I described to you, as well as something else called conditional imitation learning, failing on significantly out of distribution scenes in the CARLA simulator and the new scenes real data set. So in the CARLA simulator, actually, this is a roundabout that was never observed. We never had any expert demonstrations of what it means to drive at a roundabout at training time. So it's an extreme example of out of distribution or distribution shift, but it's illustrative. And we developed an approach to be epistemically aware and use that awareness to make better plans than the models that are epistemically ignorant. So here's a video of that extreme case. Again, there's no training data from the roundabouts observed by the models when they were trained. So our approach in green, RIP, is driving safely in this out of distribution scene. You know, if you look at the plans of the other approaches, you can see that it would be a bad idea to follow them. They are not really following the provided goals. Okay, so what do we do overall in this work? To summarize, we capture epistemic uncertainty with an ensemble of imitative models. And again, those imitative models are those models that are predicting the future of our own agent. And then we use the predictive variance of this ensemble to serve as an indicator or to indicate to either us or an algorithm when we're out of distribution. We also use this ensemble as part of a planning objective termed robust imitative planning, or RIP, which naturally integrates epistemic uncertainty into its planning. So we observe it to enable some recovery from significant distribution shifts. And finally, we could use we have an algorithm that uses the epistemic uncertainty to identify when to query the expert for additional data. Essentially, we want to collect additional data from the expert when we are very uncertain about what we should be doing. And then also we have all of this code open sourced, and as well as a benchmark of out of distribution scenarios that you can use to test other approaches in terms of how well they can adapt to out of distribution settings. I'm actually going to skip over the mechanics of this algorithm. Suffice to say, we aggregate scores across an ensemble of models that essentially enables you to do something like worst case planning. And we found this model and this overall approach to outperform the previous approach I talked about, the deep imitative models, as well as a few other approaches that came up after that. Okay. So that sort of concludes the discussion about, I guess we're just going to switch application domains right now, with the goal of producing richer structured output with the model. So the application domain here is first-person behavior modeling. The model can jointly generate discrete and continuous trajectories of future behavior. So this helps it describe different aspects of behavior. Some of them are, like motion, are best described with continuous positions. Others are best described as categorical variables. So the task here is we want to forecast human behaviors from a first-person video stream. Some behaviors, as I mentioned, like motion, are best described as these sequences of continuous variables. And things like semantic activities, like washing your hands, opening doors, etc., are best described with discrete variables. So again, we are generally uncertain about what's going to happen in the future, so we're going to model the future behavior of the camera wearer as a probability distribution over motion and over activities. This is just a way to describe in notation. What we did, we have this target distribution of demonstrations that we want to match. And I guess the main point for how we construct the model is that we factorize the joint, the Q XA given phi, into a motion prior. So just given the scene information, make predictions about how the person is going to move. And then given those predictions, a conditional that's also conditioned on the scene information to predict actions. So one thing that's a little bit different here than in the driving work is that we're also trying to identify the current positions of the agent. We're not assuming access to them, which makes sense in cases like where you have GPS in autonomous driving. We are trying to simultaneously localize the agent in a mapped environment, and then use that information as conditioning information to the prediction. The way that, I think I might have elided how exactly we perform the discrete prediction. Essentially, we're using some recent techniques on how to smoothly differentiate samples from deep generative model that generates discrete samples. I'm sorry that I left it out, but maybe you can check out the paper. We evaluated the approach on this data set called Epic Kitchens, and we had developed a few different generative model baselines, as well as a discriminative model. And we measured things like how well we could predict the future motion and activities of the behavior, and when, because some of the behaviors are discrete, we can also use these precision and recall, these information recall objectives to measure the approach. Okay, the approach we found to do pretty well. Let's see, does this include, yes. I guess I left out some of the details of this. The main point that to get across here is that when we include, if you recall from R2P2, there's this reverse term that is required, not required, but it encourages better sample quality. And we found that sort of bore out here in this case too, where including that term enables you to generate much higher quality samples. We also did something, it's not really the main focus of the paper, but where we want to continuously adapt the system to additional behaviors as they're demonstrated. So imagine the person is sort of changing what they're doing over time, and we want to adapt to it. This is generally very difficult with deep networks. You essentially don't have any guarantees. You really only have learning guarantees in terms of regret for special systems that has special parameterizations, like linear systems. And what we did was very simple. We froze all of the parameters of the network except the last layer, and found this was able to enable us to do fine-tuning of the approach in order to perform online learning. And so we did some analysis and showed this is no regret, and we did some experimentation, and it also bore out that the regret of the system does decay over time. Okay, so that was, again, the focus of that work was about the idea that when we're predicting, when we're making predictions, we want, in general, to have as rich of a forecasting capability as possible. So instead of just continuous, we have continuous and discrete. And now I'm going to take that one step further with this next approach called SPF squared. So instead of, I mentioned this earlier, instead of predicting trajectories of future motion, we're actually going to predict trajectories of sensor data. And we're going to show why this isn't completely crazy and how it's actually useful to the downstream task of trajectory forecasting. So we're going to use this structured forecasting task to design a perception and prediction pipeline. Instead of, in the standard pipeline, when you have some incoming sensor data, first you run detection to identify where the agents are, and then you use those detections to perform prediction. That's the standard pipeline. Instead of first detecting and then forecasting, what we do is we forecast in the sensor data and then detect objects in the forecasted sensor data. So why is this something that we would want to do? One reason is predicting point clouds doesn't require any labels of behavior. We don't need someone to go in and label positions of all of the agents in the scene. It just requires these sensory recordings. So it means we can scale the predictive component of the forecasting pipeline in an unsupervised way. So if we have a reliable way to take the forecasted sensor data and turn it into detections of positions, that means we can scale our forecasting performance by simply scaling the unsupervised component of the approach, which is appealing in many scenarios where it's easy to collect the sensor data, but hard to collect the labeled sensor data. So the way that we do this is fairly straightforward. We constructed this network. It's just an encoder decoder, and we treat it in this case just as a deterministic problem and supervise the predictions of point clouds according to the chamfer distance loss. One key to how we do this is the way that we represent point clouds as fixed dimensional range maps, which are essentially just like this discretized polar coordinate system of where points are in 3D space, represented as an image. So with this fixed dimensional representation, it's much more amenable to standard deep learning architectures. Okay, so we found that not only is this approach competent at predicting videos of point clouds in autonomous driving settings and robotic manipulation settings, but also when we combine this with a straightforward 3D object detector, so something that takes in a point cloud and outputs detections of positions, this actually achieves competitive trajectory forecasting approach performance on several different data sets. So without any trajectory labels, we were able to achieve good trajectory forecasting performance. We only needed positional labels. And if you have an object detector that doesn't require positional labels to train, then you can do the whole thing completely unsupervised. But we did not test this. Okay, that concludes my talk on jointly forecasting and controlling behavior from high dimensional observations. So hopefully this perspective is on control and forecasting is food for future thought. And I want to thank these collaborators. This work was made possible by them, and they're great people to work with. And now I guess we can open it up to questions, and here's some links to some of the things I talked about today. Thanks.
Thanks.